Okay, so I just want to go through a little bit of terminology for you. So a nucleon is a proton or a neutron. It's just anything that is a subatomic particle in the nucleus. We'll see nucleon used in this chapter. That's what it means. It means interchangeably a proton or a neutron. So I could say, oh, I have 10 nucleons. That just means that I have 10 subatomic particles in the nucleus. I don't really know, is it 10 protons, 10 neutrons? Is it 8 protons, 12 neutrons? I don't really know that information. I just know that it's a nucleon. It's in the nucleus. So if we think about back to Gen Chem 1, we spent a lot of time in Gen Chem 1, especially when we're talking about valence bond theory or molecular orbital theory, about the behavior of electrons in an atom. The probability map of you finding an electron in an atom is controlled by both the electron repulsive forces that we feel, but also by the pull from the nucleus, that effective nuclear pull that those electrons are going to feel coming from the nucleus is coming from the positive charge of the protons that are in that nucleus. So we have two conflicting forces that are happening on an electron. It's feeling a positive pull from the nucleus and it's feeling a repulsive pull from other electrons. In nuclear chemistry, we're only really looking at what's happening inside the nucleus, which is a really small part of that overall size of that atom. In the nucleus is where the majority of the mass is. So that's where your protons are, that's where your neutrons are. Those are adding the mass to the atom. There's a whole lot of positive charge in the nucleus. And so you think about like charges repelling each other, you should have a repelling force that's happening inside the nucleus where those protons are repelling each other. That's where neutrons are important. And neutrons are important because they're helping to stabilize that nucleus. And there's this thing called the strong force. And the strong force is responsible for binding or stabilizing the nucleus. Because if you think about it, you have the potential for there to be a lot of repulsive forces going on between those protons. The strong force is what's kind of overcoming that and allowing that nucleus to be stable. In radioactivity, when I have an unstable nucleus, that means that something has overcome the strong force and made that nucleus now unstable. And then an unstable nucleus is going to undergo some sort of nuclear event where it's either going to change a proton to a neutron to a proton. It's going to pull an electron in from the atom and turn that into a proton. So there's lots of things that are happening in the nucleus if the strong force isn't large enough to overcome the positive repulsive forces that are happening between the protons. And that's where the neutrons are important. The nucleus is a balance of proton repulsive forces and this attractive strong force, which is stabilizing. This is destabilizing. So just as electrons feel opposing forces, protons feel opposing forces too in the nucleus. And so it's the job of the neutrons to come in and stabilize everything. And they also add mass, because this is where the strong force is coming from. You can have too much of a good thing. So if I have an atom with a large number of neutrons, this actually becomes destabilizing because these neutrons have to be somewhere. So if you think about how we put electrons in an atom, we put them in terms of energy levels. So the electrons that were closest to the nucleus had lower energy. The electrons that were further away from the nucleus had higher energy. When we have neutrons in an atom, we also have neutrons in energy levels. And without going into a lot of the nitty-gritty of what that looks like, just know that as I increase the number of neutrons in the nucleus, I'm having to add them into higher and higher energy levels. As the number of neutrons increases, then I'm adding them into higher and higher energy levels. At some point, this is too high to overcome this here. So that's my stabilizing force. So if I keep doing this, I'm going to destabilize the nucleus because these forces, these energy levels are going to overcome my strong force. When that happens, now I have an unstable nucleus, and that unstable nucleus is going to move to a point of more stability by having some sort of nuclear event, whether it's an alpha decay, a beta decay, a positron emission, or an electron capture. That nucleus is going to do something to reestablish stability. The number of neutrons is important, and also the ratio between protons and neutrons is important. So that's important for the stability of the nucleus. And we could write it this way because it's a ratio, but more often than not, the way that you're going to see it written is this: neutron over Z. And so Z, remember, is my atomic number, and that's simply the number of protons. So these mean the same thing, but you'll see it written this, and this is that NZ ratio. And that NZ ratio is going to give you information on the stability. It doesn't tell you what type of radioactive decay is going to happen, but it will give you a clue that your nucleus is unstable. I'm going to look at this NZ ratio. And some of the things I'm going to look for is if my N to Z is 1, then that's a stable nucleus, and it's not going to undergo any type of radioactive decay. If my N over Z is greater than 1, then this is unstable because it's neutron rich, meaning I have too many neutrons per the number of protons. And if it's neutron rich, it's more than likely going to undergo beta decay. Not 100% of the time, but it will be more apt to undergo beta decay because remember, in beta decay, what's happening is a neutron becomes a proton. So I'm reducing the number of neutrons, I'm increasing the number of protons, so I'm going to decrease this NZ ratio. And that's going to effectively reestablish stability in that nucleus. If N over Z is less than 1, this can also be an unstable scenario. And now I'm neutron poor, meaning I have too many protons to my neutrons. And then I could undergo positron emission because a proton becomes a neutron. I could undergo electron capture because a proton becomes a neutron. So I'm increasing my number of neutrons, decreasing my number of protons, or I could even undergo alpha decay, and that's also going to help me. So in this case, I could do alpha decay, positron emission, and electron capture. And that's going to help reestablish stability in that nucleus. There is this thing called the magic number. So if I have even numbers for my number of protons and my number of neutrons, irregardless of my NZ ratio, if both of these are even, then that is going to be more than likely a stable nucleus. If they're both odd, then that's going to be more likely to be an unstable nucleus. And then if I have one even and one odd, now I'm kind of in the middle. So my stability is high up here, low down here. Only a few elements have odd numbers of both protons and neutrons, and so that's not a very common, but when you do see it, those are more than likely going to be isotopes of that element that are going to be radioactive. If the total number of nucleons, remember a nucleon is a proton or a neutron, adds to a magic number, then the nucleus is going to be more stable. So these are all magic numbers. Some other magic numbers are when N or Z, so number of neutrons or number of protons, equals 2, 8, 20, 28, 50, and 82, or 126, then those have a little bit more stability than the average element as well. So there are reasons for this. There's this thing called the valley of stability, where your NZ ratio of stable isotopes, and so you can see here that this is NZ equals 1. And so most of our radioactive isotopes are going to have an NZ ratio greater than 1. Stable nuclei do not really exist above an atomic number of 83, so your heavier elements, if they occur naturally, are going to have at least one radioactive isotope. Just because you have so many of these neutrons in the nucleus, now you're overcoming that strong force. And then this NZ ratio is going to tell you just how unstable that nucleus is going to be. So we're going to end here, and then we'll pick back up with part 2.